Hello everyone, my name is Mohammed Charawi. I'm a senior software engineer at the Extreme Scale Architecture and Development Division at Intel. And today I'll be presenting DAOS for applications, basically how to show you how DAOS can be leveraged from the application perspective using all the different middlewares and APIs that applications use today. The DAOS storage architecture is mainly focuses on the usage of the new hardware technology in 3D NAND and obtain persistent memory and obtain SSD, of course. And DAOS internally makes the decision on where to split the data. Usually all the metadata and the small data coming from the application goes into the persistent memory using the PMDK user space software stack driver, which gives you a transactional update to persistent memory, and all the bulk data goes through SPDK, which is a user space driver for any NVMe capable SSD, which also gives you good performance. So everything on DAOS from the client to the server side is always in user space to leverage the low latency and high bandwidth and high IOPS of this new storage technology. There is still, of course, between the client and the server, there is the communication layer using libfabric, which is also another low latency and high message rate communication layer, and has native support for RDMA communication and collective operation. There is also support for the different network backends. And on the client side, which is more our focus today, is the DAOS client library, which is a very low weight software stack that applications can link directly with. It has its very rich API that anybody can use, but the intention is that we want to support other existing storage APIs so that applications don't have to rewrite their codes to be able to run over the DAOS software stack. So since most of our focus today is on application side, we will start with the storage container in DAOS. Note this is something different, than Linux containers. A storage container is basically a data set, and what we refer to as a data set in DAOS. So for example, it can be an encapsulated POSIX namespace containing a bunch of directories and files organized in whatever the regular typical file system. It can be a data set that just has a flat directory with a very large number of files, which is typically what applications that do I/O on the file per process case. It can be an HDF5 file with a different organization of HDF5 objects between groups, data sets. It can be a KV store with different size keys and values. It can be a columnar database or a graph application to store the graph data set there. The main idea between a container, it's a single manageable entity. You can, instead of managing individual files or individual objects, for example, to do data movement or to do indexing or anything like that, you can take the single container and do most of the management on that side. So for example, you can have a snapshot on in your entire container, on your entire data set. You can have move your entire container between tiers, like if you have 2 tiers on a system, a DAOS on another parallel file system, you can easily move the data there by just referring to the container. And since we don't expect to have a lot of containers versus a lot of files that we have today, you can easily do some indexing to sort of track your containers on your system. And down, in a container, you can have many DAOS objects. The idea here is that POSIX is not the foundation anymore of the DAOS storage stack. There is what we provide a rich data model that exposes a multi-level KV store, and from that also it can have a flat KV store. We can have an array interface that's all available for the application to use. So what this gives you, it's not just it gives you a rich API that supports structured and unstructured data from the application side to support all the different use cases today that come not just from HPC application but also from other domains like big data analytics or high performance data analytics and artificial intelligence workloads, where most of the data there is unstructured in that sense, and using a POSIX interface to store the data is very inefficient. So over the wire, the communication between the application and the DAOS is a KV, a multi-level KV interface. So there is no serialization into a POSIX byte array and that gives, and from that we can bypass a lot of limitations that POSIX imposes if you are doing serialization and all that. Of the data into a byte array. The data is transferred in its KV form, for example, between the client side and the server side, and all small data and all metadata like keys and small values are stored in persistent memory, and larger bulk data is stored on the SSD side and indexed into the persistent memory. That gives us very fast and efficient inserts, lookups, overrides, and things like that. And it enables us, of course, to do some interesting things like in storage computing, where you can ship your if you have some framework set up, you can do some computation on the storage side by doing something close to the data rather than moving all the data between the client and servers a lot. From a user perspective, DAOS provides some tools to manage the data and manage the system. There is administration tool called DMG, or DAOS management tool, which lets you do things like storage provisioning, doing some firmware updates, and create pools for users to have like an allocation of a certain amount of size and also a certain amount of performance, collect telemetry data and whatnot. But users are mostly going to use the DAOS tool, which is more directed for users, and that lets you do things like querying how much the pool, how much data you have, how much space you have, doing some management on containers, like creating containers, moving containers and whatnot, and other sort of functionality that we will touch on during this presentation. So in terms of network and application interfaces, what does DAOS support? So today you can see in blue some of the interfaces that we have support for today, and in orange some of them that we are looking for. There are others, of course, that we keep adding more as time moves on. So today, in most cases, everything is built on top of POSIX, right? But our intention is to break that and have POSIX as one of the just as a middleware library, and support the POSIX, for legacy application on top of DAOS, but work with other middleware developers like HDF5, or middleware libraries like HDF5, MPI-IO, and others to write DAOS backends for a native implementation over the DAOS stack. So instead of having, HDF5 implemented on top of POSIX, which is still possible once you have the POSIX interface implemented, it's more efficient to have HDF5, for example, using the DAOS API directly. So adding a plugin, as we'll see, to HDF5 is going to give us much more features and much more performance than using the POSIX interface in that sense. So there are other, of course, libraries and middlewares that we have support for and are working on, like SegWi, which is more for oil and gas companies. In terms of when we talk about AI and data analytics, there it's more using towards high-level languages like Python, where we have Python bindings, and other big data frameworks like Apache Spark, Apache Arrow, and TensorFlow. And the idea, once data is in its storage format, in the storage tier, we will provide mover tools to be able to move data between the storage tier and other external tiers, whether it's on the same system or a different system. These data mover tools will be able to convert the data into its native format to be accessible, for example, through the POSIX interface on a parallel file system. So, as we said, POSIX is one of the interfaces that we wanted to support, and as I mentioned before, the DAOS library provides an API that is very rich and very flexible, but we do not expect everybody to use that API. Our expectation is not for applications to rewrite their entire I/O and storage codes to be able to use the DAOS API. We still, of course, need some migration path, and DAOS and POSIX is still very widely used as an API for storage. So we implement POSIX as a middleware instead of being the main building block for storage. And how we support that is basically implementing on top of the DAOS API something similar to a POSIX API, and we call that the libdfs layer. So this will be a very similar API to the POSIX API. It gives you the same concept of, like, we have files, directories, and the same sort of interfaces to do I/O and to do data access and query things like doing a stat on a file and on all that POSIX-like APIs. So the application can still do some changes to their code to use the libdfs, which will be much less drastic than using the libDAOS API, but the idea is that it would still require application changes. And for applications that absolutely cannot change their code, we provide a fuse daemon, what we call defuse, which is sort of exports a fuse, exports a mount point that can be accessed through the POSIX standard POSIX API. Of course, fuse, since it's built into the kernel, it will impose some overhead for applications that are using that interface. But just for raw data access, we provide an interception library that intercepts just the read and write calls that go and have them, instead of going through fuse, go through the directly. They are captured and stay in user space and go through the libdfs library. So you will get faster, and this is just an LD preload library that you load at runtime. So you don't have to change your code to use that. This will give you faster reads and writes. However, metadata calls like file creation, directory creation, file removal, and rename, they still have to go through the fuse library and incur that overhead if they are not reprogrammed to use the DFS API. There is a tutorial and a presentation that dives more into that. That will be available, and gives you some idea of what is our expectation on how people would use the POSIX support over the DAOS stack. So the next interface is MPI-IO. MPI-IO is a standard I/O interface for parallel applications, for parallel access to a file or files in general. What we did here is we've implemented what we call an ADIO driver in ROM.IO, which is instead of translating the MPI-IO calls into POSIX calls, we translate them directly to DFS calls, and this is added in the mpitch library, part of the ROM.IO MPI-IO library. It is portable to other MPI libraries like OpenMPI, Intel MPI, and other MPIs that rely on ROM.IO for their MPI-IO implementation. The files that are created by MPI are essentially POSIX files. They're the same mapping, from that DFS does, and the POSIX, the POSIX fuse. If you go through fuse, everything will be the same mapping, the same file. Essentially, it's just how you access the file, the different APIs, whether it's MPI-IO, DFS, or just the POSIX through defuse. This is all the main difference here. And essentially, an MPI-IO file, what it maps down to is basically a byte array object in DAOS. To use the MPI-IO driver, there is no application changes required. All you have to do is, append the DAOS colon to the path of the file and then the MPI-IO library will select the DAOS driver to be used in that case instead of the native POSIX driver. And next we have now the HDF5 interface. So HDF5 is a very widely used I/O interface for mostly scientific data and others data in HPC and other domains. And what that gives you is a more object-oriented, a better data model for accessing data rather than just a file with a bunch of bytes. It gives you the concept of multidimensional data sets. It organizes your data in groups and lets you add metadata to your data, like attributes on the different objects that you have. Again, the HDF5 today is implemented through the native interface over, the different the POSIX drivers, MPI-IO being one of them. So if you have support to POSIX and MPI-IO, you can still go through DAOS. But again, as I mentioned, our intention is to work with these middleware applications to have better native support over the DAOS layer. So we've added a new DAOS, what we call DAOS virtual object layer, a new connector that maps the HDF5 data model directly to the DAOS data model, bypassing the serialization to POSIX and keeping the data model intact even on the storage side. So this allows to enhancing the HDF5 library also with more features like an asynchronous interface and other support that were not possible just because of some of the POSIX constraints that we have today. The current status is that this is available with the HDF5 1.12 release. It has support for all the different HDF5 tools, and again, more support for like asynchronous I/O and independent metadata accesses that are not available with the native library also will be provided. And this is all open source and available on the HDF group GitHub webpage. So one thing to note about, with all these different formats and files that we have in DAOS, we do provide something called the unified namespace. So you can have a namespace, for example, in a different file system, or even in DAOS itself. If you create a namespace with a POSIX container, you can look at all your files there and all, even if they are in a different tier, like in a DAOS tier or a different container. So when you create a container, for example, in HDF5 or a POSIX container, you can specify a path in your namespace, and that will create a link between your namespace and the DAOS container that this file will correspond to. So when you are accessing your data through this path, then you don't have to remember any of the information like the pool, the container UIDs. So this is just like a convenience mechanism for users to keep the current codes intact without doing a lot of changes to remember some information that they probably don't need to remember. We also have a Spark integration with DAOS. So this is written as the first implementation was written as a Hadoop file system abstraction class for DAOS, and has been integrated since then in the DAOS source code. And this has been done over the libdfs, from the Hadoop file system over the libdfs transparently with this Hadoop connector. However, we see more value when we have a integration with Spark by integrating DAOS as a data source through the DAOS API directly, and through other frameworks like Apache Arrow or Apache Parquet. So this will provide more acceleration to Spark input and output applications. So also we have native Python bindings that we call PyDAOS that integrate a KV store object directly with Python dictionaries. So this is a very Pythonic API for users who are not very familiar with C and you are more familiar with high-level languages. And you can have things like iterators and bulk insertions and retrieve operations there. and we plan to support more integration with PyProp, DBM, and expose more features like snapshots and integration with other libraries like NumPy and so on. There are many resources today on the web for the different interfaces and some of documentation on how to use them, and these are some links. As I mentioned earlier, we are working on adding support for more middleware libraries to have native support over DAOS, and working with more applications to show the value of using these middleware over DAOS and how much acceleration we can get from using this new DAOS software stack. Finally, I would like to thank you for tuning in. I hope this would have given you a good idea of what we support today with middleware APIs on top of the DAOS stack. Thank you very much.